our lecture on business intelligence. Today is the 20th of March 2025. Okay, so let's continue with our, or start our journey. We saw the other day that we have a three-dimensional framework for business. Okay, so this is the social level, this is the technical level, and this is the digitalization level. And here we have three steps. We said the first step was the data, second step was creating knowledge, and third step was creating value, right? So today we're going to focus on this part, okay? So data sets can be classified into groups. They can be Euclidean if a metric, usually a distance, can be defined to describe relationships between them. And that data sets can be non-Euclidean otherwise. Okay? So let's see some examples of Euclidean data sets. The first example is a time series. Okay, so imagine you have one KPI and you measure that KPI in time. Something like the temperature of a room, or this is the time, and this is the key performance indicator. So some time, some KPI that is dependent on time. Okay? So you can measure a distance between 2 points in time, T1 and T2. Okay? So, and this distance is a metric. This means that the absolute value of the distance between T2 and T1 can be measured, okay? And this is something relevant and that we can use to recognize patterns in the behavior of the KPI, okay? So we have a KPI which is a function of time. Okay, this is an Euclidean KPI because we can measure the distance between two time points. Okay? So the second example of an Euclidean data set, this is time series is one-dimensional. Okay? Just one dimension. KPI is one-dimensional. So the second example is a black and white image. Okay, this is going to be two-dimensional. Why is two-dimensional? Because here we can let's say take two axes, which will be the positions of the pixels in the image, X and Y, and we can I don't know, get an image of an eye here, just a little eye, and then some eyebrow, and the reason why this is Euclidean is because we can identify, well, this image is created by pixels. Pixels are little units, little points in space, okay, in this space of the image, okay. Let's say we take this pixel, and this pixel is, if we make it bigger, okay, we can, let's say, recognize certain characteristics. I mean, it takes a little bit longer. I try to make my notes pretty because it's nicer to learn later if the notes are pretty. So let me paint this pixel in big. So in this pixel we find this line maybe, and maybe another line, and then the black part of the iris, okay? So the reason why, let me write it because it's important. The reason why we, let's say, recognize, and this is an important word we will use later on when we study deep learning. The reason why we recognize an eye in this image is because the pixels are organized in space, a two-dimensional space, okay? So we can recognize the iris here, this part, because all the pixels forming the iris who are black are together. If we would have these pixels scattered around the image, then we would not recognize anything, even if we would have the same pixels. So we have here on each pixel, we find that we can fill this pixel with 256 different values, okay? Why different value? Why 256 different values? Because each pixel has 8 bits, okay? This is 1 byte. And 8 bits, if you have 8 positions, 1, 2, 3, 4, 5, 6, 7, 8, you can fill them either with a 0 or a 1, okay? Each one. And because of this, you have 2 to the potent of 8 different possibilities of combinations, and this is 256. Okay, this is the reason why we have values from 0 to 255. So, but the important part here is that we can measure distances. What we're trying to say is that we can measure a distance between two pixels, okay, which is given by the equation square root of x2 minus x1 square plus I2 minus I1 square if 2 points are located in the coordinates x2, y2, x1, y1. Okay, so this is the distance between the two elements, okay, between the two pixels. Because we can measure this distance, we say an image in black and white is two-dimensional. I guess we can say grayscale, not only black and white. Okay, it's grayscale. Black and white would be only 1 and 0. All right. So, any questions so far? You can open your microphone and ask. Okay, so no problem. I guess I think I'm gonna turn on my camera. Then maybe it's better for you for the communication. So the third example would be a picture color image. Okay, so color image. This is going to be three-dimensional. The reason why this is three-dimensional is because we have 3 channels. Okay, so now we have a combination of 3 channels. One is going to be red. One is going to be green. One is going to be blue. RGB, so each pixel in reality is a combination of 3 values. Okay, so each pixel is the combination of 3 values, the RGB channels, and all RGB channels belong also to the interval 255 to 0. So one pixel is defined by 3 values: 37, 89, 210. This gives you a value. Okay, this gives you a color combination. Because we have 3 channels, okay, it's always RGB, so we don't need to say that explicitly. Okay, first red, then green, then blue. So the combination gives you the thing, but the principle of the distance is still the same. Okay, so you would measure the distance in the same way. And yeah, that would be it. Okay, so that's also an example of an Euclidean data set. So another example would be when you have a video. Is in color with sound. Sound is a time series. So you have there 3 dimensions of the image plus the time frames, okay, plus the sound. If the sound is just 1 track, then you have 5 dimensions. This is also Euclidean. So if you have olfactory signals, like your nose is capturing information, this is about I don't know, 10 to 12 dimensions. If you have haptics, so whatever you touch, your skin, okay, haptic, then you're gonna have 6 dimensions at least, because the skin can recognize heat, and if it's rough or soft, and so on. So yeah. So basically, whatever is physical, whatever happens in the world that we can touch, smell, or see, it's going to be Euclidean. So the hypothesis, by the way, the human brain our brains can okay, our brains can compute around 30 to 40 dimensions in real time, and that's a lot, okay? So the hypothesis underlying basically all machine learning almost all machine learning algorithms is that the underlying, the structure of the data set allows for the calculation of a distance. This implies there is a way to measure between points in space. Okay? So this is the hypothesis of all the statistics you have studied in your studies so far. Something that we assume to be true without further explaining. Okay? Something that we take for granted. can be true or not, can be a trick of our senses, can be something that could potentially be changed. Okay? So, but this is what we are used to because this is what our senses tells us. Questions so far? Good. This is for Euclidean datasets. And now let me give you some examples for non-Euclidean datasets. These are more tricky. Okay. So the paradigmatic example is a network. And basically, we are here in a lecture of business intelligence. The data in business takes place, almost 99% of it, in a network. Okay? When you have a logistics network, when you have a servers network, when you have a network of people exchanging information, or you have a social network of whatever happens in business happens in networks. And it's a joke that all the statistics you study deal with Euclidean datasets, but actually you're going to be dealing with non-Euclidean datasets. You're going to be dealing with networks. So we need to find a way to transform non-Euclidean datasets, networks, into Euclidean datasets. And this transformation needs to be neat and clean without losing any information, because otherwise you will not be able to make right business decisions. Okay, so this is a tricky challenge. This is what we learned today. We learned today to transform non-Euclidean datasets, networks, into Euclidean datasets, okay? Because 99% of the data generated by businesses is non-Euclidean. So in order to implement the statistics into businesses, you will need to create this transformation. Okay? So let's see, what is a network? Okay. A network in its basic configuration is a list of nodes and connections between these nodes, which we will call edges. Okay. Both nodes and edges can have attributes. Okay? So characteristics. Let me paint one little example network. Node 1, node 2, node 3, node 2 to 3, node 4, node 5, and node 6. And then let's say we have 1, 3, and 5 are this color, and then 2, 4, and 6 are this color. Okay? So the colors are the attributes if you wish. A network is defined mathematically by a set, okay, a group of nodes and edges. Okay? This set is called graph. And this word is important, okay? So a graph, when we talk about graphs, we're talking about networks. And a graph is, G is the union of a set of nodes and a set of edges. All right. In our example, it's an intuitive example, but still, in our example, the nodes are node 1, 2, 3, 4, 5, and 6 with certain characteristics. 2, 4, and 6 are light colored, and 1, 3, and 5 are dark colored. And then we have the list of edges, which goes like this: 1 to 2, 1 to 3, 2 to 3, 3 to 4, 3 to 5, 4 to 5, and 4 to 6. So we have 6 nodes and 7 edges. All right? Any questions? So networks can be directed if the edge is an arrow or undirected. If the edge is just a connection. Okay? This is all very intuitive, I think. Do you have any questions? You can also ask in German if there's something that I need to repeat. Yeah, you mean this? Yeah, that symbol means the union. So this means that union. So this means like this. You see, this is from when you are having groups. Let's say you have a group of people in A, okay, and you have a different group. In this case, it's going to be edges and nodes, okay, and you have a different group of people in B. This part is the union. Needs to have both characteristics. So in order to describe a network, a graph, we need to have both the nodes, okay, and we need to have the edges. If we only have the nodes or only the edges, then you don't have a graph. Does this make sense? Yeah, okay. Yeah, well then let's make a little note there. You can so feel free to ask anytime, okay? So you can interrupt, let's say anytime. You can just put your microphone on and just ask a question. Any more questions? I like to paint my little superhero here, so. I think that if the notes are funny and pretty, then it makes it's more fun to learn. So some people, yeah, go ahead. You mean the intersection? Yeah, actually you're right. This is the intersection. Yeah, and this is the union. I mean the union, okay? So the whole thing is the union. You're right. Yep, no problem. No, thank you. The graph is the union. You need to have both. Okay? Yeah, you're right. But this is the way to think about sets, okay? Anyway, let's continue. So here the funny question is, and I guess this question is relevant for business, is how do we quantify and compare networks? Okay, so this is something that this little guy here is going to be asking himself. We are asking ourselves that question. Okay? Why? Because if we can compare and quantify, then we can manage. Just as a joke, I'm gonna write now in it stays in your mind. Okay, try to read this. If you can compare and how do you write that? You can compare and measure you can manage. So this is a rule of business. That's why I write it in from left to right and mirrored, because it will be more difficult for you to read it and then it stays in your mind. And it's more fun to write it like this. Okay? So remember this, whenever you want to manage something, you need to compare it to something else, to the current state usually, and you need to measure it in order to compare it. Remember, okay? So we use 4 KPIs to answer this question. First KPI is called average path length. Second KPI, or APL. Second KPI is called clustering coefficient. CC. Third KPI is called degree distribution. DD. And fourth KPI is called Laplacian matrix. We use a special L there. Okay? So we are going to define these 4 KPIs. We're going to learn how to measure them. Okay? So let's start. First one is the average path length, or APL. I'm going to take always the same example network, okay? So remember this little graph we had. I'll copy it here. Not so pretty maybe, but one, 2, 3, 4, 5, and 6. Okay, so the average path length is the average distance or steps. Step is when you cannot go from 1 to 4 in this network straight. You need to go through the steps, so you need to go through the edges. 1, 2, 3, or 1, 2, okay? This is intuitive. Between the nodes, along the graph, okay? So the equation of average path length, it's called APL. It's 1 divided by n times n minus 1, the sum of all nodes to all nodes, okay? So this equation looks super difficult, but let me explain it, okay? The first part here, 1, the maximum number of relationships in a graph of n nodes is n times n minus 1. Why? Because every node has n minus 1 relationships. Okay, so if we have 10 people in our network, 10, and we take one of the 10, he's going to have 9 relationships to all of the rest. So because we have 10 people, we multiply 10 times 9, and then we get the maximum number of relationships in a network of 10 people, which is 90. Okay? So the second part of the equation describes the steps, the sum of all paths between the nodes. So we are dividing here what is the number of paths between the nodes by the number of maximum could be relationships. That's why we have an average, okay? In our example, you see the graph above, okay? This example, let's calculate the average path length. Please look at the image. Do not write right now, okay? Look at the image. You can write later. I will do it very slowly. APL equals 1 divided by n is 6, so we have 6 nodes, times 6 minus 1, okay, multiplied by. So we take node 1. I'm going to repeat, do not write right now, okay? Just look at the image. So what is the distance between node 1 and node 2? The distance between node 1 and node 2 is 1 step, okay? 1 step. Look at the upper right corner. 1 step. 1 step, okay? So the distance between 1 and 2 is 1, plus the distance between 1 and 3 is also 1 step. I need only 1 jump. Plus the distance between 1 and 4 is 2 steps. I'm taking the smallest, okay? 2 steps. I don't go through 2, which would take 3 steps. I go through 2 steps. Plus the distance between 1 and 5 is also 2 steps. Plus, so 2 steps, 1, 2. The distance between 1 and 6 is going to be 3 steps. Okay? You cool? Any questions how I did that? Yeah? Yeah, we take the shortest path. So we could go and say 1, 2, 3, 6. This will take 4 steps, but we take the shortest. 1, 2, 3. Okay? Yeah, we take the shortest. All right, so let's continue with node 2. Notice that I'm putting here little numbers, okay, just to help me remember. I am very disorganized guy, so whenever I do this, in order not to make mistakes, I try to get a structure in the equation, okay? I think it helps me get better results. All right, so 2 to 1, the distance is also 1. 2 to 3 is also 1. 2 to 4 is going to be 2. 2 to 5 is going to be 2. 2 to 6 is going to be 3. Right? So for node number 3, distance between 3 and 1 is going to be 1. Distance between 3 and 2 is going to be 1. Distance between 3 and 4 is going to be 1. 3 and 5 is going to be 1, plus 3 and 6 is going to be 2. Plus distance between 4 and 1 is going to be 2. Distance between 4 and 2 is going to be 2. 4 and 3 is going to be 1. 4 and 5 is going to be 1. 4 and 6 is going to be 1. All right? So distance between 5 and 1 is going to be 2. 5 and 2 is going to be 2. 5 and 3 is going to be 1. 5 and 4 is going to be 1. 5 and 6 is going to be 2. and distance between 6 and 1 is going to be 3. 6 and 2 is going to be 3. 6 and 3 is going to be 2. 6 and 4 is going to be 1. 6 and 5 is going to be 2. All right? So this is the way to calculate the average path length of a network. So please take a moment and calculate it. Give me the number, please. Somebody do it, okay? So what do you get? Hello? You need to divide it by 30. Yeah, no problem. So it's 50 divided by 30. This is going to be 1.67, right? All right, thank you. So this is the way to calculate the average path length. Ja, inkorrekt. Nicht weiter gravieren, aber ja. Danke. All right. So why is this important? We can compare. So imagine you're a business leader and you're designing 2 servers, okay? And you can have these 2 configurations for the server. Okay. There is only here 2 links are missing. Okay. Here this is missing. This is missing. This is configuration A. This is configuration B. You can compare the average path length of APL A and APL B. Okay. Of course, APL A is going to be smaller than APL B. And this means, I mean, you can do it, that you get information or material or money or whatever you're moving in the network faster from one node to the other in network A than in network B. Because the average path length of A is smaller than the average path length of B. Okay? So when we design business networks, we usually seek for the smallest possible average path length. All right? This is important. In the exam, I could ask, here is this network, here is this network, compare both of them in terms of speed of information transfer, and give me your recommendation for choosing one configuration or the other, and argument why. Okay, so you need to calculate the average path length for both networks, compare them, and tell me, okay, I would choose this one because the average path length is smaller than the other. All right? This makes sense? Okay, Leon says, yes, I would need some more confirmation. Does this make sense? Nicolas, okay, good. All right, thank you. So, does anybody have a question how to calculate this? Sure. Yep. Yeah. Yeah, we can, yeah, this is the simple case, yeah. All the paths are the same, yeah. No, of course. I mean, you can complicate. This is a good question. You can complicate this. Make your network design more realistic with many attributes, like we said before. Okay, so you can have not only colors on the nodes, you can also have colors on the edges. Okay, you can have different colors on the edges. Let's say some paths are one color or the other. Okay. Of course, you can make it more realistic by adding more attributes, but we are not there yet. Okay, we actually don't do that in this lecture. We are taking, let's say, a baby steps approach. Okay. But of course, if you want to if you want to investigate more about this, you could read this book, which is it's a very, very good book. I totally recommend you read it at some point in your career, because it will help you improve your skills an understanding of business and in a very deep manner. So this book recommendation is called Network Science. The author is called Barabasi. He wrote it in 2016, right? So this book is really a blaster. Okay, it's really good. So if you guys want to learn more about networks and how they work, you should definitely read that. Okay. I can reckon that you guys are wanting, like, let's say, realistic descriptions of business, okay? Because you're looking for solutions. I need to first give you the principles, okay? So please, I apologize, but I need to go step by step. Otherwise, I am going to lose like 80% of the class on the way. If I run too fast, then I lose the people, and I cannot afford that. So please apologize. And if any of you wants to learn more, you can come to me and we can discuss in detail more about any aspects you're interested on, okay? Mag die Brille nicht. Ich wollte eine schöne Brille machen. Das ist schön, oder? Machen wir die Glasses. All right. So the second KPI is called clustering coefficient. Or CC. Okay, it describes how good groups are created in the network Okay. So the clustering coefficient is called, has this equation. Don't be scared about the equation. I will explain it very soon. Okay, so just let me write it. 1 divided by n, the sum of 2 times L sub e, k sub e minus 1. So what is L sub I? This is the number, and don't be scared, okay, this is something you need to think about, number of relationships between the neighbors of node I. In other words, friends of I who are friends to each other. Okay? So this is the way to think about this. So imagine you have 5 friends. Okay? You have 5 friends. Who of these, or how many of these friends of yours are friends to each other? Okay? This is the way to think about L sub I. K sub I is number of neighbors of node I. Okay? So if we take the example network from above, again, this was like 1, 2, 3, 4, 5, and 6, I think. So the clustering coefficient is like this. Again, do not write right now. Look at how I do it. You can look at the video later and write again. So 1 divided by 6. So for node 1, the formula says 2. Okay, so it's 2 is always. Times how many friends does 1 have? 1 has friends 3 and 2. So there is one connection between 3 and 2. So this means our value here of L1, this is L1, is 1 divided by how many nodes are connected to 1? 2. So this is K1 times 2 minus 1. Okay? Does it make sense? I repeat it for node 2. I repeat it for node 2. 2 is always like this, okay? So how many neighbors has node 2? 1 and 3. How many connections between them? 1. So L2 is 1. Okay? Divided by the number of neighbors of node 2 times 2 minus 1. All right? Can anybody do with me number 3? Does anybody want to do it with me? No? All right, I'll do it. Number 3. 2 is always the same. L3. How many nodes are connected to number 3? 1, 2, 4, and 5. How many connections between them? 1 and 2. Okay? So L3 is 2. Divided by 4, which is the number of nodes connected to 3, times 4 minus 1. Do you want to do number 4 with me? Somebody? No. So Nicolas, you can do it if you want. Just put your microphone on and do it. Tell me what I should write. Yeah. Why? The neighbor of 4s are 3, 5, and 6, and there is only one connection. Very good. So wait. This is L4, and then what? Which is what? 3, very good. Okay, 4. Very good. Thank you very much. So, you guys want to do number 5 with me? Just put your microphone on and hit it. No? So, I'll do number 5. 2 times. Number 5 has 3 and 4 as connections. They have one relationship to each other. So, and there is 2 neighbors, 2 minus 1. And then number 6. 2 connections. There's only one connection, so number 6 you can forget because there is only one neighbor, so it doesn't make clusters. So can you calculate this, please, for me with your calculator? So I'm getting in my head 11 divided by 18. Is that correct? Hello? Please do it. It's important that you get some exercise with your personal calculator. In the exam, you will need speed. So how much is 11 divided by 18? 0.661 period. Okay, 611. Very good. So, again, imagine you are, thank you very much. Imagine you are leaders of an organization. The clustering coefficient measures how tight clusters or groups are created in the network. Therefore, the higher, the better usually. So we seek for maximization of the clustering coefficient. So in one example, imagine you have a group of people, you're a leader of a group of people, and you have two possibilities of putting them together. One is this one, and one is this one. Okay, so this is A and this is B. So clustering coefficient from A is going to be bigger than the clustering coefficient from A is going to be bigger than clustering coefficient from B. Why I know it so fast? Because here we have 1, 2, 3 triangles, and here only have one triangle. Clustering coefficient also measures the number of triangles you make in a network. Okay, so just it's your rule of thumb. Okay. So when you are designing networks or groups of people or whatever you're designing, when you're leaders in a couple of years, look for high clustering coefficient. When you write the exam and I ask you about this, make sure you pick the network that has the highest clustering coefficient, because this is better for sharing information or to be resilient to malware attacks and stuff like that. All right. I mean, if this is a server and node, let's say this node goes bad, you can still operate pretty easily. If this is a server and this node goes bad, you're dead. You don't have a network anymore. Okay? So clustering coefficient means resilience. All right? Any questions so far? Irgendwelche Fragen? Leon, geht klar. The rest, questions, please. No questions? All right, then let's make a little break until 9:30. 9:30 we continue, okay? So a little break until 9:30. Go grab a coffee and let's continue later. Continue, if you wish, with the third KPI. Which is called the degree distribution. Degree distribution, remember K sub I is the degree of a node. Is the number of neighbors, and node I has, okay? So the degree distribution represents the distribution of the degrees throughout the network. So let me paint again our example network. Okay, and here the degree distribution is going to be like this. It's very intuitive. This is the degree, okay, and this is the frequency, like with any distribution. So the question is, how many nodes have one neighbor? Can you tell me, please? One node, which is number 6, has one neighbor. So one node has one neighbor, and because we have 6 nodes all, we take the frequency of one node is 1/6. Okay, how many nodes have 2 neighbors? Or the way I do it, it's probably good. The way I do it is I put around every node, I do a line, okay, so I get the number of crosses to other through the edges are the number of degree, okay, the degree, so I get 3 nodes, 1, 2, and 5, because 4 has 3 and 3 has 4. So 4 was not correct. Does it make sense? 1, 2, and 5. Good. Then we're cool. Then we have 3 nodes with 2 connections, with 2 in degree. So how many nodes have 3 connections? 1, right? Number 4. How many nodes had 4 connections? 1. Number 3. Very good. So 1/6. So this is the degree distribution. This curve, okay, we would have more nodes. It would be, let's say, a lot more compact, but this curve has a sum of 1, like in any distribution in the statistics, okay? So depending on the structure of the degree distribution, we have different types of networks, as we will see in the next lectures. Okay. Very good. Any questions on this? No? I mean, it's pretty straightforward, everything, but the last point we're looking at today is the Laplacian matrix. Which is this L letter, which is a little bit weird. So the Laplacian matrix contains all relevant network information and is Euclidean. Okay? Whereas the graph is not Euclidean. Remember, we were talking a few hours ago how we are looking for. The big question is to get to transform non-Euclidean datasets into Euclidean datasets. Okay? This is a big thing for you. And this is what we do with the Laplacian matrix. First, let's look at the definition, okay? L is defined as D minus A, okay? So D is the degree matrix, and A is called the adjacency matrix. Which can be defined mathematically as K sub E if E is not J, or 0 if if E is J, or 0 if E is not J. And the adjacency matrix is defined as 1 if connection between I and J, and 0 otherwise. So this is just the math. Forgive me for having to describe it with mathematical terms. As you will see in the example, this is as easy as drinking a glass of beer, okay? So no worries, it's going to be super easy. So let's take our example network. Let's describe the Laplacian matrix in proper manner. And now again, do not write, just look. So we have 6 nodes, 1, 2, 3, 4, 5, and 6. So the degree matrix, which is the first one we're going to look at, is a diagonal. So because it has the degree of the node when E equals J, so in the diagonal, and 0 otherwise. So the degree of the node 1, the number of neighbors of node 1 is 2. Number of neighbors of node 2 is 2. Number of neighbors of node 3 is 4. Number of neighbors of node 4 is 3. Number of neighbors of node 5 is 2. Number of neighbors of node 6 is 1. And all of the rest of the matrix is zeros. Okay, so this is the degree matrix, which has the degrees in the diagonal. Is that cool? All right. Minus, we take now the adjacency matrix, which is, does 1 have a relationship to 1? No. That's why we put a 0. Does 1 have a relationship to 2? Yes. We put it 1. Does 1 have a relationship to 3? Yes. We put a 1. Does 1 have a relationship to 4? No. We put a 0. Does 1 have a relationship to 5? No. 0. To 6? No. 0. Understood? 1, 2, 3, 4, 5, and 6. Understood? Questions on how I did this? Does anybody want to do the second row with me? No? All right. Well then, 2 has a relationship to 2, yes. 2 has a relationship to 3. Well, no, wait. Let me put it this way. Does 2 have a relationship to 1 in that direction? No. So we want to say this is a 0. Does 2 have a relationship to 3? 2? No. Have a relationship to 3? Yes. Does 2 have a relationship to 4? No. 2 has a relationship to 5? No. 2 has a relationship to 6? No. All right? So does 3 have a relationship to 1 in this direction? No. So that's a 0. Does 3 have a relationship to 2? No. To 3? No. To 4? Yes. To 5? Yes. To 6? No. Does 3 have a relationship to, does 4 has a relationship to 1? No. To 2? No. To 3? No. To 4? No. To 5? Yes. To 6? Yes. To 5? And node number 5 has no relationship outgoing, and neither has 6. Okay? So our Laplacian matrix turns out to be like this. Still, do not write, just look. Okay? So this number minus this number. 2 minus 0, 2. Again, this number, 0 minus this number. 0 minus 1, minus 1. Again, minus 1. 0, 0, 0. Next row. 0, 2, minus 1, 0, 0, 0. Next row. 0, 0, 4, minus 1, minus 1, 0. Next row. 0, 0, 0, 3, minus 1, minus 1. Next row. 0, 0, 0, 0, 2, 0. 0, 0, 0, 0, 0, 1. This is a Laplacian matrix. We're all cool. Any questions? So this is D and this is A. Okay. Any questions? Did you understand how I did that? Yeah, was not too fast. No, good. So the fun fact is that this Laplacian matrix has the same information as the graph. The same, but is Euclidean. So we can do stuff with it. The graph, the picture, is this. The graph, nodes and edges, has the same information as the Laplacian, but the Laplacian is Euclidean, so we can do stuff with it. The first thing we can do is we can discover bottlenecks in the network analytically. Okay? So if I would ask you what is the bottleneck of this network as we have it, what would you say? What is the bottleneck of this network? Three is a bottleneck. Why? What? Why? No. Yeah. What do you see? Yeah. So if three fails, we don't have a network anymore. Yeah, but not that easy as you said. I explain it now, okay? So the eigenvectors, you can see it in the eigenvectors. The eigenvectors of the Laplacian matrix contain information about its partitions. So a disclaimer, the eigenvector, the way to calculate the eigenvector, you should know from math. The eigenvector looks like this. So if you have a matrix like A, V are the eigenvectors and lambda are the eigenvalues. Okay, so first you do the determinant of A minus lambda E, and then you calculate the eigenvalues, and then you have the eigenvectors. So if you have the eigenvectors, the second, this is the key here, the second eigenvector of the Laplacian matrix is called Fiedler vector, and has a symbol structure that helps find the bottleneck. Okay, so the second eigenvector, the Fiedler vector, has a structure like this, always. First has pluses, then zeros, then minus, okay? So these are the nodes. So positive numbers, 0, almost 0 numbers, and then negative numbers. So where you have the first node, where the zeros start, then there is the bottleneck. That's the node bottleneck. Okay? So in our example, 1, 2, 3, 4, 5, and 6. In our example, the Fiedler vector is going to be like this: positive, positive, 0, negative, 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 negative. Okay, so this is going to be node 1, 2, 3, 4, 5, and 6. Okay, so the the bottleneck is going to be the node number 3. All right. So the question asked by, I think it was Nicolas before, yes, you can see it in the Laplacian, but not so easy. All right. So questions on this? What do you want? How to calculate the eigenvectors? Okay, you should have seen this in math in the first semester. Okay, well, if this is the case, then look at it, okay? The calculation of the eigenvector, this is basic algebra. I can give you an example, but it's basic algebra. Imagine you have, I mean, we are in a business intelligence lecture, not in an algebra lecture, okay? So imagine you have a matrix like this. Okay, so this is your matrix. Then you have the determinant of A minus lambda E needs to be 0. So the determinant of 1 minus lambda, 2, 2, 3 minus lambda needs to be 0. This means that 1 minus lambda multiplied by 3 minus lambda minus 4 needs to be 0. This means that lambda square minus 4 lambda plus 3 minus 4 equals 0. Okay. You solve this, lambda squared minus 4 lambda minus 1 equals 0. So lambda takes the values of 4 plus minus 16 plus 4 divided by 2. Okay, so 4 plus minus square root of 20 divided by 2. So you get lambda 1. I'll take a calculator. Square root of 20 plus 4 divided by 2. This gives you 424. Lambda 2 it's square root of 20 in minus plus 4 divided by 2. This is minus 0.24. So these are your two eigenvalues, okay? And then you take the first eigenvalue and you say A 1, 2, 2, 3 multiplied by your first eigenvector needs to be your first eigenvalue, 424, multiplied by your first eigenvector. Okay, this gives you two equations. V11 plus 2V12 is equal 424 V11, and 2V11 plus 3V12 equals 424 V12. Okay. So with these two equations, we can calculate the coefficients of the eigenvector. We multiply the first one by minus 2. So we have minus 2V11 minus 4V12 equals minus 848 V11. And 2V11 plus 3V12 equals 424 V12. Okay. And this goes like no, wait, I need to solve it differently. Not so fast. Like 2V12 equals 324 V11, and 2V11 equals 124 V12. Okay, basically it. And so you can calculate the V11, V12. Okay. You do the same for the second value, which is minus 0.24. And you get the coordinates of the second eigenvector. So the eigenvectors, what they are describing in this context is if you have a network of nodes, the eigenvectors of the Laplacian, they are describing how you can partition the graph in clusters. Okay? So they are basically describing the directions. This is one cluster. This is one cluster. This is one cluster, and so on. Okay? So they're giving you the second eigenvector is giving you the bottleneck, because it's giving you the point in which the symbolic structure is changing. Of course, I don't know who asked. Who was the guy asking? Nicolas. You don't do this with pen and paper, okay? So don't be too worried right now if you didn't see this in the algebra lecture, because the way to do this is with a computer, okay? But still, if you didn't look at eigenvectors and eigenvalues, you need to do it, okay? So, yeah, well, then you should have. And if you are talking to people, who gave you the math lecture? Okay, I don't know the guy, the girl. You should have, okay? So this is very important for Wirtschaftsinformatica because it gives you a lot of information about data sets, okay? The eigenvalues, eigenvectors. Look at it into your, later in the semester, we will make some calculations with this. So look at it into some algebra books, okay? This is very important. We will do it actually in the later part of the semester when we do the principal component analysis. This is an algorithm to compress images, so we need it. Okay. Good. So with this note, I guess. We have the KPIs that I wanted to see in this lecture today, okay? So any questions? We saw, as I said, 4 KPIs. Apologize that I wrote in mirror. I think sometimes it's fun. So any questions?